So for this question, we're asked what should be the value of k for our gain controller that's in the front here, if the steady state error is to be less than 0.1 for a unity step input. Now it doesn't explicitly state it, but I'm also going to put in here that we need the system to remain stable as well, because our steady state error equations only make sense if we have a stable system. If your system becomes unstable, then you're not even able to calculate the steady state error, so it's definitely a requirement, even if it's not explicitly stated. So let's go through first of all and look at what the requirement would be for steady state error, and then we'll look at what the requirement is for stability as well, and we should be able to make then an overall statement on what's required for the steady state error to be 0.1 and our system to be stable. Alright, so to look at our steady state error, I'm going to do it using the error constant method. So for that, we need to know the open transfer function for our system and judge the system type from it. So open transfer functions are what's on the top line when you're not considering the feedback loop. So the open transfer function is going to be this block times this block times this block. Alright, so we can judge the system type quite easily now. What we're looking for is on the bottom line, any S's that are on their own. So we can see that we've got S's tied up in here, but they can't be factorized out or anything because that's a constant on the end. Yeah, that's all tied up as well. So basically we've got no S's on their own or no integrators. So therefore, it's going to be a type 0 system. Alright, so I've pasted us the little table in here. So we're focused on a type 0 system, so that's going to be this row. And we're looking at a unity step input, so that's going to be this column. So this here is the cell that we need to evaluate. We can see it's the one that's got a finite value, so we're going to actually have to go to the effort of calculating our KP error constant and then using this equation to convert that into the steady state error. So let's go calculate KP. So the equation for it is the limit as s goes to 0 of our open transfer function. So subbing in, I don't think there's anything that can cancel top and bottom lines, so I'm going to now sub in my limit, which is when s goes to 0. So I'm left with 5k times 3 and 2 and 1 on the bottom line. And this here ends up working out to 15 divided by 2k, which is the same as 7.5k. Change this into our steady state error, and we have the equation from the table. Remember that this is for a unity step, and in fact we have that. It tells us we're looking at a unity step input, so we can just directly copy it. We don't need to multiply it by the size of our step. So that becomes our expression for the steady state error in our system. So now we need to look at the requirement on our steady state error, and that was that we want it to be less than 0.1. So if we go back, we can say that 1 on 1 plus 7.5k here, our steady state error, has to be less than the 0.1 requirement. So we should be able to now rearrange this equation in order to get k needs to be bigger or smaller than some number. So if I take the 0.1 and divide it down to the other side, I'm going to get 1 on 0.1, and I'm going to put this up to the other side at the same time. I'm now going to take away the 1, so this becomes 1 on 0.1 is 10, 10 minus 1 is 9, and then we can figure out k is going to be 9 divided by 7.5, which is equal to 1.2. So if you want to flip this around, we're going to find that for steady state error, to meet the steady state error requirement, this needs to be true. K needs to be larger than 1.2. So now we need to go and check what happens with the stability of the system. Do we have any extra requirements which are going to change what this needs to be? So our stability calculations need to be done with the closed loop or the overall transfer function. So let's call it G closed. We should be able to calculate it. We can see that our system is a negative feedback system, so it's going to just be our general equation that we need to apply, which is G open on 1 plus G open times H, where G open is what we found before over here and used for our steady state error, and H is what's in our feedback loop. And we can see that we have unity feedback, so therefore H is just equal to 1. So if we want to get our closed loop transfer function, since we have unity feedback, we can shortcut it. We know that this equation is going to simplify to our open loop transfer function, which I'm just writing now. Okay, copied from here. And when we close the loop, we end up with whatever's on the denominator whatever's on the numerator being added to the denominator as well. So that becomes our closed loop transfer function. Now, to be able to perform our Ruth table calculations, we need to expand out the bottom line. So top line doesn't really matter. So expanding out this though, we end up with that. And I'm going to try and make it look a little bit nicer by factorizing my different powers of s. So I've only got one s cubed term. I end up with a total of 4 s squareds. I've got a couple of things for s. I've got 5 in total here, plus I have 5k. And for the constant, I've got a 2 and a 15k. Alright, so now let's go ahead and draw our Ruth table. Using the bottom line here, the highest power is s to the 3. And filling out our constants. Get that. And if we need to, we can label everything else with zeros as we keep going across. So we need to go through and figure out this first column and check we don't have any sign changes. So far so good. Both of these are positive. So we can work on the third one here. So let's give it a little name so I can work it out at the side. So it's going to be the negative of the determinant 1, 4, 5 plus 5k, and 2 plus 15k. And it needs to be divided by the pivot element, which is equal to 4. So expanding this one out, it's going to be equal to this. Okay, so it would be the negative of this times this minus this times this. I've already put in the negative in this line here and expanded it out, and it all gets divided by 4. Right, I don't think I left enough space in here to try and transfer this over, but you can just remember that this goes in here, and we're going to need to develop what the requirements are on k in order for this cell or this expression here to remain positive, but we'll do that in a moment. So now we'll just focus on this last box here. In order to work it out, we need these two and these two for the determinant. This one's pretty easy. Its determinant will be 1, 4, and 0, 0. Whenever you have these two zeros on the right-hand side, you end up with a 0 for your cell of interest. And when we come down here, whenever we end up with a 0 in the right-hand bottom side for the determinant, we end up carrying down the top right side element. So this comes down here. And of course you can prove that to yourself by doing the maths like we did over here. So again, we have a k in here, which means that we're probably going to be able to put a requirement on what k should be in order for this cell to be positive. Alright, so let's start with working with this one. So we need all of these things to be positive to have no sign changes in our first column. Alright, so this is this, which is this cell. So it needs to be bigger than 0 for it to be positive. So let's go through and rearrange this. I can multiply 4 up to the other side, and 0 times 4 is just going to be 0. So that eliminates that part. And at the same time, I'm going to expand this out. So we're going to get 20 plus 20k minus 2 minus 15k. Has to be greater than 0. So if I put the two k's together, I'm going to get 5k, 20 minus 15. And I'm going to shift both of these constants over to the other side. And for that, we're going to end up with negative 18. So k on its own is going to be negative 18 divided by 5, which is some negative value. And what we can conclude though is overall, k just needs to be bigger than 0 in order for our system to be stable, because a negative gain just doesn't make sense. Alright, you're going to design your system to have a positive gain, because for example, if it's like the velocity of a motor, if we end up putting a negative k I should say, into our transfer function up here, what would end up happening is that if this was negative, we'd end up swapping the sign of our output as well. And if it was, like I said, the velocity of a motor, what it would mean is that your motor would then start turning the opposite direction, which doesn't make any sense at all. So anytime you end up with your stability calculations, k being required to be greater than a negative number, you can just adjust it up to be that k needs to be greater than 0, because that makes far more sense. Okay, so now we've got one other cell that we need to deal with, this one here. So in order for our system to be stable, 2 plus 15k has to also be bigger than 0. Oop. We're going to end up, if we flip this over, that 15k has to be greater than negative 2, or that k needs to be greater than negative 2 on 15. Again, this is a negative number, so we can adjust it to be 0 for the same reason as negative gain doesn't make sense. What we've got left is to put together all the requirements that we've just developed for k. So these two ended up being exactly the same, that's just a coincidence. So we know that k needs to be greater than 0. We also have the one that we had before, which k needs to be greater than 1.2 in order to meet the steady state error requirements. So overall, if k needs to be greater than 1.2 for steady state error, and k needs to be greater than 0 for stability, what we're going to say is that this one kind of gets overwritten by this one, because we're going to have a stable system even if k is, say, 1. However, if a k is 1, we're not going to meet this steady state error requirement. So overall, the answer to our question is that k just needs to be greater than 1.2, because we're going to have a stable system and our error is going to be less than 0.1 for the unity step input. So that's all there is for this question, and I'll see you in another video.